essentially this is the same kind of thing. You're going to be proving things about general rules for series, essentially, like sums and things like that. Basically, it comes down to mathematical induction is a method to go about finding a proof for a certain statement. But if the statement for these things, and for you guys, is going to focus on sequences, series, and maybe what numbers to do. So proving things kind of about numbers. And writing like general statements. Like general statements being like the sum is, 3n plus 3 or something like that. All right? And essentially, guys, you got to understand, the reason behind this is just to get you in the habit of understanding that if you ever get to the point in your mathematics career, whatever you're doing, any kind of class beyond this, and you have to write any kind of argument about like a set of numbers or about how numbers react to each other, they're probably going to ask you to prove it. All right? Because they want you to be sure about, without reasonable doubt, that this has to be the correct answer. This is something that I know gets used quite a bit. It's not going to be the only way you do proofs. In here, probably in terms of proofs, this is probably the only one we're going to get into, at least for a while. And it's the reason this might get used a lot by people is because it's actually a very easy way to do them once you get the hang of it. Okay? It's not like geometric proofs, guys, because you're not looking back on theorems. Here you're relying simply on algebraic manipulation to prove your point. So in essence, all you're doing is solving equations, making them equal to each other. Okay? There's just a process you have to go about and certain things you have to write out.
Can I turn that thing off? A little bit, 'cause, like,
Yeah, that's not good. Okay, now, basically what I've already said is what's up there. Your steps, in terms of doing a mathematical induction proof, are going to be, they're going to give you a statement. Okay, it could be something like, I don't know, k or n squared plus 3 is always divisible by 3 or something like that. And you have to prove it. You're always going to follow 3 steps. Okay, the first step is always going to be you're going to show that it works for k equals 1. Like I don't have it up there yet, but I'm going to write these out. All right. Then you're going to, once you show that it works for the first term, you're going to assume it works for everything. So this is going to be one of the only proofs where assumptions are going to be allowed where you can go, oh, I assume this is going to happen. All right. That's why this is sometimes called proof by assumption. And then what you're going to do is use what you're assuming to be true to work for you in order to show that the next term would be true, which would be the k plus 1. All right? So saying it with words seems weird. I understand it's probably like you have no clue what the heck I'm talking about. Okay? But when we start doing the problems, it'll fall a little bit more into place. Now, so restating this. Restating this, these are the 2 conditions that you're working for. Your first step is always going to be taking whatever the statement is, and remember, you're working at this as if it's like the first 2 I'm going to do are going to rely strictly on certain series. And then the last one's going to be a little bit different. There's going to be 3 examples and all. But your first step is always going to be make sure the statement that's given to you works. For 1. Like if I took 1 and plugged it into the formula, it gives me the correct answer. Once that works, like if that doesn't even work, you would stop. But if the question's asking you to prove it, that should always be something that definitely works. But it's just a check. Once you show that, then you assume that it works for the first k term. Okay, and what the point of doing that is you're going to create an equation. All right, or you're going to show in a series something that you're going to take and plug into the last step, which is showing that k plus 1. All right, so both of these things have to happen for induction to work. You have to have the first thing work, and you have to have the second thing. All right, now, again, I haven't done any examples, so you writing this down and trying to figure out what the heck's going on is not going to make much sense. Okay, okay, until you actually see the work being done. Yeah,
What is the K?
it's the letter K. Literally, you just take K and plug it in. You're gonna, with the K part, you're creating equations. Because the whole point of this is you're working algebraically to manipulate things so that the K would create an equation with it.
Wait, but like the P would be.
Yeah, you'll see.
Okay.
Don't, that's what I said. It's not gonna make too much sense just looking at it in terms of, all right? So there's 3 of these we're gonna do. This is gonna be the first one. I'll go as far as we can to the south. All right? Definitely agree. All right, so this would be an example of what they're giving. There's a sequence up there. It's defined. This would be like you've taken this sequence and you found out that that is the general rule for the sum, okay? That's essentially what's being represented there. They're saying, look, if I take the first n numbers and I find the sum of them, I can always just take however many terms I'm doing and square it, and that's going to come up with the sum. So essentially, that's you're just going through some steps to prove that that would be a true statement. So you're saying if I added all these up, it's always going to be n squared regardless. All right, so your steps. First thing you're going to do. All right. First thing is that. Okay, so you're assuming you're going to do work to show that P of 1 is a true statement. And remember that the P here, that's n equals 1. And when you do it, don't use the actual equations they have there. Like on this side of the equation is the term. So 2n minus 1 is what I'll plug that in. So what I'm checking is I'm checking to see if 2n minus 1 equals 1 squared. I'm just taking the 1 and plugging it in. So that's always the first step. Because if this doesn't even hold up, I can't move past it. All right, so if I do this, I get 2 minus 1, which is 1, correct? So I get 1 equals 1. That's fine. Okay? The next thing is you go, well, since P of 1 is true, you need to kind of write this out in terms of like a proof. You got to understand you're explaining it, so you do need to write it out like sentences in between linking things together. So I would say something like, all right, since I know P of 1 is true, I will assume that. All right, so I'm saying, hey, look, if it works for the first term, it's going to work for all of them regardless. All right, that's the assumption part. And what you would do is now you would write out what this is. All right, so if I wrote out what that P of K is, and understand the K, guys, is what the N is. All right, essentially what you're doing, the point of doing this part, say you're creating an equation with a variable other than the N, because the N's already accounted for up there. All right, so if I wrote this out, PK would be like 1 plus 3 plus 5 plus all the way to 2K minus 1. Okay, and basically what you're doing with this step, you're saying that anywhere I see this sum, like something up to this term, I can essentially take this out and replace it with this part, because these are equal to each other. And that's what you're going to do. This is like right here, essentially what you're doing is you're creating something that when I get to the next step, I'm going to take this whole section, take it away, and replace it with that. So you're creating two things that are equal. Yeah.
I don't understand how K squared is equal to the 2K minus 1 because
it's not. K squared isn't equal to 2K. Like K squared is, this is the sum of the first K term. I don't know where K is. And this is also the sum of the first K terms. It's just written out with every single term separate.
But like 2K minus 1 is like for each term. That would be like the A of n.
Yeah. Yes.
Okay.
Yeah. All right. Now, the next part is going to be called your inductive hypothesis part. We're going to go, okay, I'm assuming that's true. Now, what I'm going to do is I'm going to write out a statement for K plus 1. Okay, so this will be the next term. All right, so if I did the work and I wrote it out, Like if I just took it, so what I'm saying is I'm taking this step right here, and I'm adding one more term to it. All right, so what it would look like, 1 plus 3 plus 5 plus. All right, everything I just did, and now I'm adding the very next one to it, which would be plus 1. Right, because to get to the next term, you're always adding 1 to whatever's in the parentheses. So now this would become 2k plus 1. Okay, just looking at the left-hand side. All I've done is I've taken what I had here. I'm adding one more step to it using the rule that's up there. Yeah.
So your k can be any number.
Yeah, and I don't need to know what k is. I don't care what it is, because when you prove something, you're proving it for any number ever. So I don't need an actual number here. I want it to stay a k. Like I want that. All right, and then on the other side, so now I'm up to k plus 1 squared. So again, all I've done is I've taken the k plus 1, right, and I've plugged it in for my 2 that I have here. Now, the point of writing this again, okay, is because right here, where I assumed that all of this was true, I also said, look, anywhere I see that, I can just take that away and replace it with k squared. So I know, in essence, right here, I can eliminate all this and just write k squared, because I know these two are equal to each other. All right, so when I do that, what's going to happen is now I've got essentially an equation happening. And now I'm going to do like distributing and stuff all at the same time. Because what you're going to end up doing, like once you're to this step, to actually prove this, really all you're going to do is try and get both sides of the equation to look the same. You're going to make them equal to each other. All right, so if I do my distributing here, it would be like 2k plus 2. Is that okay so far? Like I just expanded the other side. I just did some distributing. All right, so I know, look, this side of the equation is pretty much already taken care of. I know that's what it looks like expanded. There's nothing else I have to do with that side. So what I want to do is I want to try and make this side look like it. And hopefully they will when you just combine like terms and stuff. All right? So if I just kind of combine like terms, 2k is there, plus 2 minus 1 is, they're the same, correct? Okay? That'd be good. That's what I want. Okay? That basically proves that this works. So then you would say something like, it would say, the way you write it is you go pk plus 1 follows pk, meaning that I've just basically showed that they are in order. Everything checks out. All right? And you say thus. It's called the principle of induction. This event is true. That would be like the whole problem. Okay? That's probably the bare minimum in writing you would have anyway. I kind of skip through some stuff and I write sentences shorter than I probably should, but that's it. All right, so look. This one, guys, if you don't understand what that says, that okay, don't like the way the computer loaded it. All right, so going through, what's that?
That's so confusing.
It looks weird though. All right, so going through the steps again. Okay, still doing the all induction. I'm still trying to see if this works for every number ever. Step 1 would be show that it works for n equals 1. Okay, so again, don't do it with like 5. Actually, do it with the formulas they give you. So it'd be like 3 times 1 plus 2 equals. All right, which do both sides of the equation equal 5? Do that. Check them for me. I assume they do, but I don't.
They do.
They do?
I don't know.
It should be. They do 5 equals 5. Okay. 3 plus 7 be 10. Divided by 2 be 5. Okay.
That's not 5.
How are you getting
Oh my God,
11?
I can't even write that.
How are you getting 11?
3 times 1 is 3 plus 7.
Move closer. Because I need all the space.
Oh.
3 times 1 is
3
plus 7
10.
times 1.
Oh, times 1.
No adding there.
I got
Yeah.
it. Day to day.
All right, Amy. Okay, now, since, all right, so next step. Since you know that's true, okay, now this is where you're going to assume PK is true. Okay, and remember, write it out so that you can actually see it as, in terms of the ones with the series and stuff, because the next one's going to be a little different. Write out the entire series, like when you define it. So when you, and again, that's a step where you're just defining what PK is. All right, so 5 plus 8 plus 11.
So you just write what they already have?
But remember, you're plugging in K.
Oh.
That's all you're doing. You plug it in so that you're showing that you're actually doing it for a number. It's just any number you possibly want. Hold on one second. All right. Yeah.
So will we always be 1?
You always start with 1. The very first thing you do is always that first step.
Like what
What do you mean?
will it ever be something the same?
For that first step? No. This part will always be 1. Always. Okay? It's just the easiest one to check out of all. I can check whatever number I want, but 1's always the lowest one, so it's going to be the easiest to check. And the higher number you get, the bigger number you get.
So for the second part, all you're doing is putting K or
Yes. And again, the whole reason of that is when you get to the next part, when you go, okay, now I'm going to do P of K plus 1, you're technically writing all this out again, because what you're doing is you're doing the next term after this one. So I'm saying, okay, I've already got all this stuff accounted for in the step before, now I'm going one more step, and that's K plus 1. So now you're just taking that and plugging it into what's up there. So this would be 3, K plus 1.
I don't understand that.
What's that?
I don't understand how to do that step. I don't understand.
But yeah, why are you moving? Oh,
Okay, again, the whole point is to make sure this works for every number ever.
what if it doesn't?
Okay, so what I'm doing is, it might not. I mean, if they're saying prove it, the assumption is it's going to work out. And if you don't get it equal, you screwed something up. You might run into some that
don't work?
that don't work. It might be, if they ask the question in terms of, is it possible that, like where they don't flat out say prove it, then you could have a yes or no. Okay, so the assumption is you're assuming this works for K term. So what you're trying to do is show that it works for the next term. So the K plus 1 is the very next term. All right, I'm not assuming that works. I'm just going to do the work to show it. All right, so again, now, once you know this part, again, the whole point of writing it out this way is so that when you recognize that this and this are exactly the same, you can remove that from it and put this there, because this part and this part are equal. So anywhere I see this, I can replace it with the K parentheses 3K plus 7 over 2. All right?
Wait,
Yes?
why did you add the, like, why didn't you just make it 5 plus 8 plus 11 plus the 3K plus 1 plus 2? Like, why?
Because I want to see, I write this step out so that I can actually show that this whole thing I've already defined up here. Like if I don't show, if I eliminate that, I can't technically do this step because I'm not demonstrating that I'm removing the exact same thing. So these two are exactly the same. Anything that's exactly the same, I can remove and replace with what I know is equal. I know these two are equal, so that means where I saw this, I can take it out and put that.
Yeah.
But, and the point of doing that is now I can eliminate the 5 plus 8 plus, because I don't know how many terms are in between there. I don't know what numbers are
No, I
added.
get that those two are equal, but I don't understand why, like, I don't
I have
understand
to
why
show
you're
it being
adding.
exactly the same.
I know, but like, why are you adding the?
You're saying, like,
two?
that's
No,
gone?
that little.
This
yeah,
part?
That. Why is that there?
Because you're putting in the K for the,
Well, I understand the K plus one, but.
you're plugging it in.
I have to show up to however many terms I go to. So if I go up to K plus 1 terms, this thing better stop at
Oh,
K
yeah,
plus
so
1.
like in the first one, you see how it's just P and K, there's nothing added to it?
Yeah.
So you just substitute the K where the N goes. Does that make sense?
And then two starts equal to K
Uh,
times 3, K plus 7, and 2. Be another example.
I'll get it. You just have to.
No,
add
don't
it.
worry about that. Afterwards, I'll try and tell you. Oh, there. Alright, so this is 3K plus. Is everyone okay with what I just did there? I I distributed what I could. I did basically one step in every thing. Like I want to show all my work, but I'm just doing as much as I can on each.
I don't know why, but I really did.
All right, now here's the thing with this one. Remember the whole point I want you to hear is you want this side and this side to look exactly the same. Which means you're working in terms of combining lead terms, doing algebra stuff. Make things as easy as you can. By that I mean, in this step right here, if I see fractions, try and get rid of them. It's usually easier for people to work on a single level instead of the 2 level. So I would take everything and multiply it by 2. Because if I multiply this by 2, I'm just left with that. If I multiply that by 2, it becomes 6K plus 10. Correct? Is that okay?
Yeah.
Right, because 3 plus 2 is 5, plus 2 is 10. And then if I multiply this by 2, I'm just going to be left with whatever's on top. Okay, now look, there's 2 ways I could go about this. On the right-hand side, I've got something that's factored out, right? I've got 2 binomials there. I could work with this side and get it down to factored. Or I could multiply this stuff together, combine like terms, and then on the other side just multiply those together and get like a trinomial. And that would be another approach. Do you want me to factor this side? The easier one would be expanding it.
All right, expand away.
Okay? Because there's less work to do, because all you have to show is that each term is exactly the same.
On the right side, put your 3K plus 36.
No. I did. This is all on top, so when I multiply by 2, it just gets rid of it.
Oh.
All right, so if I multiply and like combine my terms and stuff, like if I multiply these together, that's 3K squared plus 7K, correct? Right? I did do that correct, right?
Yeah.
Okay. If I multiply these together, what does that give me? Okay, 3K squared plus what? Okay. Fine. All right. So the last thing would be, if I combine the other terms here, 7K plus 6K is how much? Are those exactly the same? That's what I want. Okay, and again, the whole point of doing this part, so now that I've showed that, look, if it works for one term beyond K, which I don't know how many K is, it could be 100 out here. This will work for every term beyond that. I don't have to show anymore. All right, so you would say, you would just write it out again. PK1 follows, or plus 1 follows that, thus, by the principle of induction, it works for all n. Follows. Okay. second one. The next one's going to be completely different though. It's going to be the same kind of thing, but I'm not going to be doing a sequence on them.
Same kind of thing.
The process is the same. It's just like this is going to be different. Okay?
But I like this. I like this too. I didn't think I would, but I like it.
That's the next one.
I don't think I've ever sat in math class and said, I like this.
It's a good glare, so I can't.
It's like, we see on this, it's like right there.
On there?
Yeah. So no one's going to know what happens in here. It's just magic. Just happened. Can I erase all that stuff? Is that right? Yeah.
It's pretty simple forever.
It is. Writing it out properly takes the time.
That's why you're only giving us like 5 problems tonight,
Sure.
Yeah, really, are all these gonna take like 10 minutes?
right? Yeah, they really will.
It's not like that. It's not long.
Oh,
And I don't think every single problem is actually.
Only 20 questions in
Okay, so here's the thing.
Right.
The whole assumption here, you don't have a series or anything, but they're giving you a general rule still, like n cubed minus n plus 3, and they're saying that that is divisible by 3 no matter what number you plug in for n. Okay, so what it's asking you to do is prove it. All right, so you still do the same steps. You still go, okay, so you show that, and again, this is like P of n right there, that thing right there. So that's technically how you need to think about it. So you're still going, okay, I'm going to show that P1 is divisible by 3. Because that's the whole idea here, is you're showing that it's divisible by 3. I'm no longer doing like 2 sides of the equation, I'm just working with things being multiples of 3. All right, so I would take my 1, plug it in, right? So I get 1 cubed minus 1 plus 3. All right, which 1 cubed minus 1 plus 3 is how much? 3. And I would hope you go, okay, 3 is divisible by 3, right?
No.
What?
Definitely not.
All right, see we go. Okay, that checks. 3 is divisible. All right. Okay, well, since I know that works, I know the first term works, that means it's probably going to work for all of them. So you would again assume
The assumed one has gotten steadily shorter. The first one you wrote the whole thing out, and the second one you wrote like half of it.
oh, no, I wrote the sins thing, I just didn't do it. All right, so my next step is going to be I'm going to assume that's divisible by 3. And you got to think in terms of that, divisible by 3. I'm not going to have equations. All right, so what I'm basically saying is that k cubed minus k plus 3 is divisible by 3. So anywhere I see that grouping of terms, I can say that part of my equation is divisible by 3. Okay, you got to keep that in mind when you're doing this. All right, now, we'll k plus 1. Now this is just a matter of work. I'm going to plug in k plus 1 and try and manipulate it so that I can get everything matched up as divisible by 3. Hopefully what you should do is while you're working on it is you should find this somewhere in there. Because if I see those 3 together, like k cubed, just looking at it is not necessarily divisible by 3 because I don't have a 3 in front. Neither is this. But if I see these 3 things together, I can group them together and say that bit is divisible by 3, and then whatever's left over, you would hope to show as a multiple of it. Like in this case, 3, could be 2, 1, whatever. All right, so that's what I'm working with. I want to show that that part is divisible by 3. All right, so I'm looking for multiples of 3, so like the actual number 3, or 3 in front of a term, or something like that. Or I'm looking for this, if I can. So you have to expand this, if there's no way around it. So I need someone to expand that out for me. Tell me what it should be.
Yeah, it's a lot of work.
No, not really. If you don't remember the process, do it as like that. It's k plus 1 squared, you should be able to multiply out.
How do you do that?
We just did it on the, wait, this was what? K squared? Thank you. Plus 1. All right. So all this was I rewrote this here. This was multiplying it out, and I distributed that negative through there just so I have it.
You just take off that whole middle.
What's that?
You just take off the whole middle, right? Just take plus 1 minus k minus 1.
It's like you're missing something right there.
Well, we just k minus k and then 1 minus 1.
I do.
So you wouldn't feel like simplify it?
Well, as long as the work is done correctly as of right now, then that would all make sense.
Well, it is, so.
Be sure.
Yeah.
Someone else check. Someone else needs to check.
I volunteer.
From here to here.
Oh, yeah.
I'm just going with it. I mean, is it
K
100%
cubed
correct?
plus 3. Yeah.
All right.
I feel like I feel the same way. I think when I was a kid, like, I knew everything and I had it all figured out, and now I'm like,
No, I
super
mean, all, I
teenager.
mean, you can tell it really now.
What? Say. What?
Hey, what is this weird radio?
I got 3K. That's what I got, 3K. Sabrina, why aren't you checking this?
Thank you.
I volunteered you.
Yeah, come on. All right.
No.
That's where it should be. Okay.
Are you sure?
I don't know. We'll find out. All right. So here's the thing. Okay. So essentially, the way this works, guys, is what I'm going to do is I'm going to rewrite this. Okay, so that I've got this part grouped. So I'm going to take this k cubed right at there, this minus k right at there. All right, and that plus 3, put it there. Okay. So that I've essentially, what I've done is I've taken this part, put it up front, this part, moved it there, and this part. Now, the reason I did that is because I know this grouping right here is divisible by 3. So I can already say that group of things is divisible by 3. All right, so I've essentially worked with that one, and that one. Now, after it, the rest of the stuff is going to be just me combining the other like terms. So like I've got plus 1 here and minus 1. So plus 1 and minus 1 go away, correct?
Yeah.
It's gone. All right, so the two things I'm looking at that one, which I've already set up here, that is, oh my God, divisible by 3. Are those two have 3's in front?
Yeah.
That means they're divisible by 3. Okay? If I've got both of my sections divisible by the same thing, that checks out. Okay, I've basically proven it there. I said, look, this part's divisible by 3, so is that. That means the whole thing is. That's how fractions work in. Okay? And then you would write the end part. You'd say, okay, pk plus 1 follows pk. All right, thus by the principle of induction, I can say that it works for all values of n.
Work.